Okay, so the next speaker is Matthias Meiwes from Tel Aviv. And his talk is about linking in horseshoes and 3D Reeb flows.
Thank you very much. First of all, I would like to thank the organizers for inviting me to IMPA and to Rio. It's my first time. Okay, so today I would like to talk about some recent results, partly joined with Marcelo Alves, Lucas da hinten, and Aubry-Mather, about some properties of topological entropy for Reeb flows that are special for Reeb flows. And let me start with some motivation, which also serves as an example for later. So let us look at geodesic flows of surfaces. So we look at the geodesic flow on a surface. So let's first think of sigma as a higher genus surface. So there's a lot of things I can say about the dynamics, but let us look at periodic orbits, or number of periodic orbits. And then it's classical, and by now not so hard to see. So if I look at the homotopy classes of geodesics, I find a lot of them. And the best way to express this is with growth properties. So there's, for any G, the number of homotopy classes which carry periodic orbit grows exponential growth of periodic orbits. Pairwise non-homotopic. So exponential growth in the period. So this holds for any metric G, but what happens if we take the two torus? So then two different kind of dynamics can appear. We have some dynamics with some hyperbolicity, some integrable dynamics. So for example, if we take the flat metric, we have rather few periodic orbits. So there are many periodic orbits, but few that we can really distinguish. Few periodic orbits. Let me be not so precise. But for others, so let us look, for example, the flat metric, and let's plug in some bump. So G bump has suddenly we create many. And how can we think about these many? So let's maybe look at the universal cover. Okay, I could go on like this. So let's look at some strip like this. And let's label some lifts of this path between two bumps to the cover and label them the upper ones here like 1, the lower ones 0. Then for any periodic sequence in 0, 1, I get geodesic with lift in the strip, and the pattern is given by this sequence. So, for example, this one here would be the lift of the geodesic of 0, 1s. Yeah, so for each I get a closed geodesic. So that's how I think about many. I get like an exponential growth of different pattern of geodesic. So one way to think about this in a general context is to talk about entropy. Let me, for completeness, give definition. So this is, let's say we take any flow on a closed manifold. And so this is a number in 0 infinity. And how do we define it? So if we have a epsilon and a small epsilon and a t, we can look at any set in M, not necessarily periodic points, and we can define what means that they separate along the flow. So there are epsilon t separated. So this set is separated if for all x, y in x, x not y, the distance up to t so the distance between phi tx and phi ty at some point between 0 and t is bigger than epsilon. So then we call this set epsilon t separated. The metric doesn't play a role for what is coming, and then we can define the epsilon entropy as the exponential growth of the maximal number of separated set. And then we let this epsilon to 0 and get the topological entropy. So in our examples, it is known, one can see, that the entropy here, by using these many geodesics, is positive. And one can show that for the flat metric, the entropy is 0. And for the bump metric, by an argument using this coding, one sees that the entropy is positive. So this example, the torus, like sufficient conditions for positive entropy, like this bump condition or similar, were studied by several authors. So it goes back to Bungert and Winowitz, Bursztyn, and Kniepers, Glasmachers. Knieper, Glasmachers. Yeah?
So in this torus case, you have to take the bumps sufficiently.
The bumps have to be sufficiently big. So there's small bumps. Okay, I didn't say what the quality of the bump, quantity of the bump is. So if there's a sufficiently big bump, I want to say, then you have even a contractible geodesic here. But entropy you get already with a small bump. But there is some kind of threshold. It's not so.
So the entropy you would get it just with a small.
There is some threshold. It's not so.
Okay.
there's, I think, some threshold that you have to go up. This is, so I think the Rabinowitz and Bursztyn, they have a certain quantity. Then they can get a lot of heteroclinics, get a lot of orbits. Yeah. Yes, and so there's a lot of, like this bump condition is sufficient condition, but it's not so clear if I say I have on this geodesic flow positive entropy, does it come from some geometric condition? So at least as far as I understand, it's not really so clear if topological entropy in this situation is coming from something geometric. So it is, yeah. And okay, in this direction, I want to say something. So note that, yeah, as I said, if you have a big enough bump, then you have a closed contractible geodesic. And this closed contractible geodesic, it lifts to a link with two components in the unitangent bundle. So by going, so imagine here you have some geodesics and geodesic, and by taking both orientation, it gets a link in ST2. And then I can, instead of looking at, then I can try to understand periodic orbits in a complement of this link. And in this direction, one can think, and this is, okay, say something more later. So this all has a flow homology, or a Reeb flow story. So it turns out that a lot of this type of questions, it's very good to look in general for Reeb flows. And this started with the work of Leonardo and Schlenk, and then Marcelo Alves studied this extensively. The case where the contact structure itself induces for all Reeb flows positive entropy. So this is the first kind of equivalent to the first example. And then there's also the story of when both things can happen, zero entropy and positive entropy. And there's a nice paper of Alves, Pazov. And what they are looking at is the contact homology in a complement of a link. So let me say something about this. There's the cylindrical contact homology. Contact homology in a link complement. This is theory due to complement due to IMPA mean. And they look at the so-called homotopical growth. Homotopical. So, roughly speaking, what is cylindrical contact homology? So you fix a contact, so you have a general contact manifold, context-free manifold, say closed, and we fix the contact form, so alpha contact form. And we assume, we choose a link of periodic orbits, closed periodic orbits. For the Reeb flow. So it's a finite collection of periodic orbits. And one assumes that alpha is so-called hypertight in the complement of L. Just say in words, so hypertight in the complement of L is a condition on the periodic orbits in the complement of L, namely that they are non-contractible in the complement of L. But it says also something about the periodic orbits that sit in a component of the link. Namely, if I want to contract them, then along the contraction, I have to pass the link, to cross the link. Okay, so this condition given, then for nice homotopy classes, row of loops, we can define the cylindrical contact homology. It's a set2 vector space over, so denoted by L, rho, alpha. So nice, I just say in words, nice means that in this class the Reeb orbits are non-degenerate, and the representatives, loop representatives of rho cannot be arbitrarily close to a component of the link, and they are not multiple covered. And then one defines the contact homology, cylindrical contact homology, generated by Reeb orbits in rho, and one counts, so the chain complex is given by counting in the symplectization of M holomorphic cylinders, finite energy, that are asymptotic to representatives, so Reeb orbits in rho, and they do not touch the trivial cylinder over the link. Okay? They do not intersect. And then one, this is almomean, and one then counts homotopy classes. Say NT is the number of rho such that rho is nice. So contact homology is defined. CH is non-zero. And the periodic orbits are all less than T for the gammas which lie in rho. And the growth is the exponential growth. Homotopical orbit growth. Homotopical growth is the exponential growth of this number. And Alves and Pianapazov exploit this growth and some invariance properties of this growth and get some nice theory. But what they asked also is, can we recover the entropy of the Reeb flow, the given Reeb flow, by this growth, by these growth rates? Okay, and the first theorem I state today is that this is indeed possible if the link, if we have already a link which is hypertight in complement. So assume there exists a link such that alpha is hypertight in the complement. Let me, for short, just this call HT for the contact form alpha. So alpha has a link with this property, then if the entropy of the Reeb flow is positive, then there exists a sequence of links of periodic orbits such that gamma of Lk converges to H top. So in some sense, so I asked for the T2, is topological entropy geometric? So we found out topological entropy is topological. Then, so in fact, gamma L alpha bounds the entropy from below. So, for example, yeah, this was proved by Meiwes-Pazov. So in fact, so then it means that if HT holds for the contact form, then the supremum over our gamma L is equal to L periodic orbits is equal to the entropy. So we have like some description of entropy with quantities defined with holomorphic curves. And this is, in some sense, very similar, or some sense similar, to recent results of Cinelli, Victor, and Gurel, Victor and Bursztyn, and Marco, Victor, and Bursztyn, that relate the entropy with the so-called barcode entropy, which looks at action filtrations. But here, we look at quite something similar, as different. We look at holomorphic curves in complement of some cylinders over links. So it would be interesting to get beyond this both inequalities, some relation. And another remark, so if there exists a global surface of section, then hypertight condition is satisfied. So then there exists a link that is hypertight in the complement. So if it's not disk-like, you can take just the binding. If it's disk-like, you add some of it. So then by the recent results of Umberto and Colin, Denoir, Rechtmann, and Marco, and Contreras, this condition here is C-infinity open and dense. So then, so HT holds. So this was mentioned by, these results were mentioned by Umberto. Open and dense. Okay. So now this is in fact quite useful, this description. Namely, if we look at some robustness of entropy in a very symplectic kind of setting, so robustness. So for this, I look at something, some distance of contact forms, very similar to what Oliver talked yesterday. So if I have two contact forms, they both are supporting xi, then I can write one as a function of the other. So it's a graph over, say, the other. And I can talk about C0 distance between them is the maximum over log fx. So this is symmetric, and it looks at in the same similar picture as we had yesterday. So if we write the other one as a graph over the other, it looks like they are close. They are close in the C0 if I can make a tube around one containing the graph of alpha prime. So for robustness features in respect to this distance, this is the following I want to point out. So if alpha is close in this C0 to alpha prime, since the direction of the Reeb vector field depends on the differential of alpha, I cannot say anything about the closeness, at least of the direction, of the corresponding vector fields. So this makes it already. This makes it like a very geometric notion, and dynamically is not at all clear what happens if I perturb my dynamics from alpha to alpha prime. But nonetheless, our second theorem, so this is together with Meiwes, Dahinden, myself and Pazov. H top is DC0 lower semi-continuous. At all contact forms alpha such that HT holds. What does it mean? Okay, I take the entropy, the function alpha goes to H top of phi alpha t. Yeah? And so by this strong results about the existence of global self-sections, we have then that H top is lower semi-continuous on a C infinity open then set of contact forms. And we get also something for geodesic flows, which was not clear before, that the same holds for of matrix Riemannian matrix on surfaces. Yeah. Okay. In the second corollary, I look at the entropy of the geodesic flow, and there's an analogous C0 distance for geodesics for Riemannian matrix, and I have this. I will say something about this. Yeah. Okay, so yeah, we have here this HT condition. So this is unfortunately there. In the surface case, I studied this also with Marcelo. And somehow the equivalent notion in the surface is the Hofer metric. And we got, without some condition, we got that H top is lower semi-continuous for Hamiltonian diffeomorphisms on surfaces. This was generalized by Michael Hutchings to area-preserving surface diffeomorphisms, also with no, also everywhere, lower semi-continuous with respect to the Hofer metric. Yeah, and here, as we already saw in the Reeb flows, things get sometimes trickier, and we have this condition, okay? Then an interesting corollary, so that has no, that's where we get rid of this condition is if we look of our example, yeah, on the space of Riemannian metrics on T2, then we don't get lower semi-continuity, but the next best thing, namely that we have robustness everywhere. So h top bigger than 0 is VC0 open. Yeah? So lower semi-continuity means that at this point we have a small neighborhood where it's positive. But this holds everywhere if we have Riemannian metrics on T2. So this is very Riemannian. So how does this follow? So if there is...
Sorry, but the previous corollary is the fact that you have global surface of sections for an open dense set of a Riemannian matrix.
Yes. Yes. So if there's no contractible periodic orbit, yeah, then we are hypertight. We don't need any link to be hypertight. So then we can just apply theorem 1. If there exists a contractible periodic orbit, then we project it to a contractible geodesic on T2. So it is known that a contractible closed geodesic induces positive topological entropy. This is a theorem of Denvier-Mackay. And that this thing is C0 stable, that the existence of a contractible closed geodesic is C0 stable, and we discussed in earlier work. So this is one I think just needs the energy function and some variational techniques of the energy function. So the existence here is C0 stable in the metric, and then we have Denvier-Mackay theorem. But this is really geodesic flow, and in T3, this argument for Reeb flows doesn't really go through. So it's even, yeah, cannot work. Okay, so let me say something about the methods. So the big thing is why we can approximate entropy is Kattok's theorem, where we approximate by horseshoes. But one has to do a bit more than that. But let me recall Kattok's horseshoe theorem, horseshoe approximation. Result theorem. And I take there's a proof which is some parts is a bit different, and that we use here is Kattok-Mendoza's proof. So this is for surface diffeomorphism. So let lambda be a surface, and f a general Hölder continuously differentiable, so C1 plus alpha diffeo. on lambda with positive entropy. So then there exists a horseshoe. What does it mean? So for all epsilon fixed, for a fixed epsilon, there exists a compact hyperbolic. So I need hyperbolic, say Fn invariant set. I mean, we get also F invariant sets, but let's write it like this. This Fn invariant set for some iteration n. And what else? We get a coding, namely we get the bijection between, so let's be that k, and we get a bijection of the space of infinite sequences in, this is a small k, in small k symbols. These are all B-infinite sequences in 1 up to k, and we get the continuous bijection on k such that the dynamics on k can be described with a shift map. So this is the shift, the left shift, say. And okay, we have a usual metric here, so we can talk about continuous map. And the entropy is close by. The entropy of the on the horseshoe is close to the nth iteration, the entropy of the nth iteration of f, which is n times h top f minus epsilon. Okay, I am not going to describe the proof, but I want to say something about how this horseshoe, how this compact invariant set looks like. So in fact, so what do we have here? I'll just make a picture. So you have in lambda, I have some rectangle here, Q, and I get some smaller, say, vertical rectangles. As many as symbols. And I have the property that if I apply Fn to one of these Qi, then it is close to a linear hyperbolic map. It squeezes two sides and stretches the others and crosses over the Q and crosses all Qj for ij k. So we have something like this. This is one of the Fn Qi. And then, having this, we get the coding. So this, the invariant set is given by all points that stay in the union of Qk for all iterations, for all multiple iterations of n. And the coding, we can think of it as follows. For every point, the associated sequence here, we get, if we look at iterations and where they land in which Qi's, yeah? And inverse iterations, where they land in which Qi's, and then we get the symbols. So this we want to use here. And for that, we need some flow version. So the flow version, it depends which setting you're looking at. Depends how easy it is to lift the proof of Katok. So if there is a global surface of section, then a variation of Katok's proof goes you can do it on the return map of the section. If you don't want the existence of global surface of section, then we have to deal with discontinuous Poincare sections. So then this is done in more generality by Lima and Henrique. So for general C1 plus alpha flow, there's the work of Lima and Henrique, where they do actually more the generalized result of Henrique for diffeomorphisms, where they get not approximately the entropy, but the full entropy in a coding. Okay, let me just say like this. So the coding is then not a shift on finitely many symbols, but a shift on countably many symbols. But nonetheless, this works very neatly. I mean, this works very well with these discontinuous Poincare sections, and we can try to get like Kattok's results from this more general theorem. So the first step, okay, then let me just, okay, so for outline proof of theorem 1. So first step is, and this works heavily with this theory, so there exists a union of disks, union of transverse disks to the flow. Disks, which such that okay, lambda is a Poincare section, by which I mean that every point in M hits lambda infinitely many times in the future and past, and hence we get a return map which is discontinuous, but nonetheless Kattok results holds, Kattok result holds. Okay, holds, there are some adaptations here, but almost the same statement for F lambda being the return map. And now comes one important thing. So this is usually not considered if one looks at this horseshoe. But what I don't want is, if I look, I mean, I have this nice horseshoe picture after n iterations, yeah? So I get all the rectangles stretch after n iterations over the other rectangles. But what happens in intermediate iterations? I don't want to see some rectangles going over this Qi, sort of partially going over. In general, Kattok is not considering that, but one can actually do that. So Fj Q doesn't intersect Q for 1 less than j less than n. Okay? Okay, so this is already very good. And then we need a second step. Now we need our link. So how do we get our link? Okay, I want maybe just there are these in horseshoes. There are these nice things, nice surfaces, which are called Fried pair of pants. So this is the following. So there are these Fried surfaces, a pair of pants. So in the section lambda, I have some rectangle which I call D because it's more diamond, and I have a, say, label this V minus, H minus, V plus, H plus. And I have the property that after some nth iteration of the return map, so this lives in lambda, after some iteration of the return map, V minus maps to H minus, and this point is a periodic point. So I have FL of V minus, and the same for plus. And if I have this, this property for some L in N, then I can build a pair of pants, which is this freed surface, which is taking D and gluing in the sides, which the image of the flow of the sides until I hit again my D back. So I take E minus, E plus. And this is a pair of pants. The binding is given by a periodic orbit here that goes through this. So this point, a periodic orbit that goes through this point, and a periodic orbit that goes, that oscillates, that goes to this point, through this point. And there are plenty of them in horseshoes. So we can find also some freed surfaces. So we find one large freed surface. And many small freed surfaces. So the large surface is F. In the section, I have like my D, and then I find like small ones, and I get similar picture as before. M, so M small freed surfaces. So here I want my iteration to be equal to n, my iteration of the freed surface being equal to the iteration where the horseshoe appears, and here I want the iteration to be 2n, because what I want and what happens for the nth iteration, I want to cross. So this will be Fn di. So I want di sits in D, D sits in Q, my original horseshoe rectangle Q, and the Fn of the i's, they sit, they cross on dj, and okay. So by this, I can see that these surfaces that I get, the F1 until Fm, they are pairwise disjoint. They're not disjoint to F, but they're pairwise themselves disjoint. And I can now play a coding with them. So I get a horseshoe here. And the link that David asks is then given, is David demanded to know? It is given by, so L is then the union of the boundaries of F and the big seed field surface and the small seed surfaces, and plus the one which I had at the beginning, the hypertight one, which I need to define contact homology and complement. So if I add this, if I add some components to the link, I stay still hypertight, and I take these unions. And then I just claim the following, because it is kind of the final line. So all periodic orbits in that horseshoe. So I want here, I get a horseshoe. All periodic orbits in that horseshoe are pairwise non-homotopic. So this is easy to see, since I intersect the free surface orbits positively, and the order of my intersections determines my homotopy class. Yeah? But then I also have to want to know what happens to the orbits that stay outside the horseshoe, but they happen anyway to intersect these rectangles. Can this happen? So no other periodic orbit in the complement is homotopic to a horseshoe orbit. How do I see that? So I have some periodic orbit. It will intersect these surfaces. Say if it is homotopic to a horseshoe orbit, it has to intersect the surfaces, these rectangles D1 and Dm in the same order, say in n intersections. But if it is homotopic to this horseshoe orbit, it has then to also intersect the big surface n intersections. But then it cannot intersect this big surface outside of the smaller surfaces. So if it intersects, say, D1 in the first time, then since after n iterations D1 maps back to D, it has the second time to intersect already the second symbol, and so on. And so I see that in fact it has to be a horseshoe orbit. Okay, so are there questions to this lengthy explanation? Okay, so just to say something about the robustness. Okay, so the robustness. Okay, so we have alpha. So we now have alpha to be nice, hypertight, and we have a link. We have a link such that the growth is close to the entropy. And now we want to see for alpha prime close to alpha. So say alpha prime is close to alpha. We want to see also some growth and hence entropy. Yeah. So by actually Yonding's theorem on entropy, it's enough to look at alpha prime that are not only close, but also C-infinity generic. It's enough to look at the C-infinity generic set, then set. So it's enough to look at alpha prime non-degenerate. So all periodic orbits are non-degenerate. And then we can look at the symplectic cobordism. So we have here here we have the symplectization of some shift, say, of alpha, and here down we have alpha prime. And okay, so to relate, so here we have this link L, and we want to find the link here, and then relate also the growth somehow from here in the complement to the complement here. So if we could, for some method, so that's actually for surfaces in yeah, surfaces we do something like this. If you could find cylinders, non-intersecting holomorphic cylinders that are positive asymptotic to the link, negative asymptotic to some new link, we can hope that we can also, in a complement, relate kind of the contact homology in a complement, contact homology complement here. But this is not quite what we managed to do. What we manage is we get some holomorphic, finite energy holomorphic curves, which has probably several punctures. Something like this. Okay, my pictures not so things. And we can also have, so we can have more components. We get some link here, but we can have more components. But it can also have less components, so we can have something like what we call a collapse. So we can have negative asymptotics that are multiples of the same orbit. Okay, so this we get by choosing epsilon small enough according to the action spectrum and taking starting with the simplexation and then plugging in more and more of alpha and look at the limit, the breaking at the limit. So we get a level. Working out this, we get some level like this. So then we want somehow to see still a lot of growth here in the complement. So for orbits in the complement of the link in some class rho, we also get something similar. So they can also collapse here to some components. And to deduce, so there are probably several methods to do. But what we're doing is, we know here we have exponential growth in the complement. So if there's no collapse, we use also we can get that there's exponential growth in the complement. But if there's a lot of collapse, what we are doing is we look at intersections at some way far down and use asymptotic properties. So we use the Siffring asymptotic formulas by Richard. And we intersect curves at some levels S cross M. And for S way much down. So we take, in the complement, we take finitely many curves, say first, and then we choose our S way much down. And what picture do we get? What picture does one geometrically get if one looks at one, say, limit cylinder, what happens close to the limit cylinder? We get a braid. So in a neighborhood of so let me just make a picture. So what we get close to the limit, we get some braiding. And these are very special braids. These are torus braids that are like cabled torus braids. And using this property, one can actually show that, there's no growth, no exponential growth. So if there's collapse here, there could only be somehow quadratically many guys in a complement collapse down. So the exponential growth is preserved. Okay, thank you.